How's everybody doing tonight? My name is Matt Russell. I'm the president of the Colorado Springs Astronomical Society.
We don't care, Fran.
Fran. Welcome to our November meeting. Don't mind the characters up here in the front. Welcome. We got a big night. We have Dr. Fran Bagenal from UC Boulder here today. Before she starts with her presentation, I got to go over a couple of announcements first. We're going to do some new member introductions. Fran's then going to do her talk. Then we're going to do abbreviated observing reports. We're going to take a break. If for some reason we don't get to, or Fran doesn't get to all the questions, hopefully she can stick around for the break and answer some questions for you. After the break, we're going to do a What's Up segment. I think Vince is in the house somewhere here. We're going to talk about the different committees that we have and a couple of exciting things that are going on there. But first, I'd like to introduce our executive committee. Again, my name is Matt Russell. We have Jim Urim, our vice president. We have Fred Goodman, our secretary. Jill Furman, our treasurer. Vicki Kitzman, our librarian. Going to be member at large? No, secretary. I'm sorry. Is Tom here? No, not that Tom.
Oh, the better Tom.
Our new member at large. George White is not here tonight. Scott Donnell and Floyd Glick, our trustees, are around here. So thank you for all your service. What I'd like to first start to do is ask if there's anybody new here tonight, and if you are new here, if you wouldn't mind, just please raise your hand, and we can figure out who you are, ask why you're here, and what you expect from astronomy meeting. So, if one of you would like to go, that would be great. So you can introduce yourself to us.
I'm Jan Parnelli.
Stand up, you gotta see it.
Jan Parnelli, and I saw this announcement on Facebook. And we recently, I think with your organization, did a thing up at Mueller. Was that you guys?
Probably, yeah.
With the planets and the fun. And just have an interest in that. I'm a sort of semi-retired nurse. Served in the military.
All right.
And we're venturing towards retirement.
All right, well, welcome. Thanks for coming.
Hello, my name is Casey. I've been sort of wanting to come to a meeting for a little while, but kind of because of time constraints, haven't been able to. So,
All right.
I'm a high school student at this Discovery Canyon.
All right. All right. Well, thank you very much for coming. Just one thing to remember is that we have some visitor cards, or the visitor cards are in the back. If you wouldn't mind filling one of those out so we can get a hold of you after the meeting and put you on a list.
Especially make the email legible, please.
Busy the writer.
Great. Anybody else? Yes.
Zach and Betty Wenner. We're both new to the area and also new to the club. Just moved here, active duty military, got CSAS here from Northern Virginia, so nice to have some dark skies again.
All right. Thanks for having me. Yeah, right on.
Yeah. Make sure they get these things.
Yep, the attendance sheet's in the back as well for members to sign. Couple notes. December, there is no meeting. We have no meeting here at the Space Foundation other than our Christmas party, which is about, a week and a half away. George White did send out an email to all of active members regarding to see if you're coming, your body counts, and what you would be bringing. Remember, there's a white elephant gift. So if you have not gotten back to George yet and you're planning on coming, please get that email out to him soon so we can have the numbers ready for the Space Foundation, because they do a bang-up job for us over in Area 51. January. We're going to talk about January's meeting right now. Real quick, there was no speaker in January. Typically, at the January meeting, we do a show and tell of all of what people have purchased over the last year or bought themselves for the holidays or whatever. So but just remember that. That's what's going on in January.
Fran?
It's a show and tell.
You have to ask your husband first.
Okay, is Walter Warren? I don't see him. Well, I wanted to bring up Walter Warren. He informed me at the last meeting that he is no longer going to be able to do badges for the club. And he's done them for years. So if next time you see Warren, please thank him for his years of service in doing that. Doug Cook will be taking over the badge creation for the club. So, so that's good. Jill and Jason, can you please come up here? Accoutrements.
Come on.
Well, you come up here too. I wanted to bring Jill and Jason Furman up here. They are moving away.
Yeah, we're going to Oregon. And I'm not sure if we're going to stay there forever or not.
But what I wanted to do is I wanted to recognize Jill and Jason for the work that they've put in over the last however many years, and especially this last year with Jill being our treasurer and Jason being our Starry Meadows head. So as club president, thank you.
Hey, not to make this goes on too much longer, but the past 7 or 8 years, I mean, this has been another family for us. And the impact that this family has made on ours is been tremendous, frankly. And we will miss you. You will see us most likely at least once a year. RMSS is a fun 20 hours drive. Hey, it might pop up in one of the.
People from Germany should come.
Yeah, so it's not goodbye forever or anything like that, but we will definitely miss you and the experience there. So thank you very much for being a part of our life.
So the treasurer is leaving unexpectedly.
No accounting irregularities.
Yeah. Well, I do have some good news, and that is that Barry Young has decided that he wants to take over the Starry Meadows Committee chairmanship. So thank you. And we are looking for a treasurer to replace Jill come January. So if that is a position that you're interested in, please see me at the break or speak with probably Scott, our trustee. That would be good, and then we will be figuring out what we're doing from there. That's all the announcements I have. So Jim, you want to take the floor, please?
All right. So tonight, our guest speaker is Dr. Fran Bagenal, and she's a research scientist and professor at the University of Colorado Boulder. She's a co-investigator and team leader of the plasma investigations on NASA's New Horizons mission to Pluto and the Juno mission to Jupiter, which is actually going to be the topic of her presentation tonight. Her main area of expertise is the study of charged particles trapped in planetary magnetic fields and the interaction of plasmas with the atmospheres of planetary objects, particularly in the outer solar system. She was born and raised in the UK and received her bachelor degree in physics and geophysics from the University of Lancaster, right? I say that? In England, and her doctorate degree in Earth and Planetary Sciences from MIT. She spent 5 years as a postdoctoral researcher at Imperial College London before returning to the U.S. for research and faculty positions in Boulder, Colorado. She has participated in several of NASA's planetary exploration missions, including Voyager 1 and 2, Galileo, Deep Space 1, New Horizons, and Juno. Ladies and gentlemen, Dr. Fran Bagenal.
wall.
It's New Horizons.
It's New Horizons. And do you know when New Horizons is going to be? New Year's Eve this year.
That's the ultimate
Ultimate. It's going to be flying past this small thing called MU-69, informally called Ultimate Thule, but it's a small, chunky little piece of ice that we're going to fly by and take a bunch of pictures, which should be really cool. So you have to wait a couple of days before the pictures come back. It's a long way. Remember that 4.5 hours one way. I think by now it's 5.5 hours one way communication time, so we won't get the data back until New Year's Day. So you can celebrate New Year's Eve, and then, you know, when you've got over the fuzziness, have a look at the TV. That's the TV, and you should be able to see it. So that'll be cool. Okay. Couldn't resist having to put that in there. So we'll go from New Horizons that explored the smallest planet in the solar system, well, one of the smallest planets in the solar system, and we'll go to the biggest planet in the solar system, Jupiter. So I'm going to turn off the lights and tell you about what we're going to see there, what we have been seeing and what we're going to see for the rest of the mission. So Jupiter, as you know, is the largest planet, and just to give you a sense of how big it is, here we have for the Earth the scale, so 11 Earths across the diameter of Jupiter and 318 times the mass of the Earth. So this is a really big, massive, big planet. And if we stretch it out and look at this planet, you see these belts and zones, the blue, sorry, not blue, orange and white stripes, the persistent weather that we see, as well as the great red spot. Obviously they're in the middle, but we've also observed for about 400 years since we started using telescopes. Now, when we look from the Earth, we get to see Jupiter just as the belts and zones, and very little else we can see. We fly by with a spacecraft like Cassini, and we can make a movie of the weather system that we have at the bottom. And I've shown the weather system of the Earth above to give you some sense of comparison. And you get to see these various features. We also have belts and zones. There's fewer of them here on Earth. And you can see places where these belts and zones interfere with, they sort of run into the land masses underneath. And so it disturbs these east-west belts and zones. Now with Jupiter, there's no land underneath. It's all a gas giant planet. And so the belts and zones just keep going around and around. And so you have turbulence in between, turbulence in the middle, and as we'll see with the Juno images, turbulence everywhere. And then we have a whole bunch of these storms, these eddies, that we will be looking at. So this is a comparison to give you a sense, similarities, belts and zones, similarities in terms of hurricanes, but obviously a much larger scale in the case of Jupiter, and more persistent weather system on Jupiter. So what are we actually looking at? When we look at Jupiter, what we're really seeing are the topmost layer, which is ammonia clouds. So not water like we have in our atmosphere making the clouds on Earth, but ammonia. And the ammonia makes these white clouds. And then when you have UV light from the sun interacting with the gases in the atmosphere, you make these sort of brown, gunky, orangey colored clouds. We don't really know what they are. Could be phosphine, could be sulfur compounds. But over a period of time, those dark materials accumulate. So the dark areas are indication of old areas. The white areas, the clouds, are indication of fresh clouds. Now underneath the ammonia, we believe there's a layer of ammonia mixed with sulfur, and then below that water. And this is the idea that we had when we sent the Galileo probe into the atmosphere of Jupiter. And we were looking for these three layers of clouds. That's what we expected, but this is what we saw. Very few clouds as the probe went in. And the reason for this is, it turns out the probe went out into a very dry area, lacking water. We know where it went, and using an infrared picture from the Earth, we can see that's a hot region, so glowing very bright in the infrared. And so the question is, was this just a hot downward draft that happened to be where we went, or are our ideas about the amount of water that's in Jupiter totally wrong? So water is very important because our ideas of how the solar system formed depend on the idea that if you move away from the sun, it starts to cool off. So in close to the sun, you're going to have things that condense at high temperature, rocks and metals to make the small terrestrial planets. You get beyond the frost line, you're going to make the cores, and when you get a big enough ice ball, lots of big snowballs coming together, so about 20 Earth masses, so that's a really, really big snowball, you're going to pull in hydrogen gas to make the gas giant. So that's our idea of how the giant planets form beyond the snow line around a core of ice and rocks and metals. Now we know that if we look at the cosmic abundance of elements, and we can simplify it, the astronomer's table up here, you can see hydrogen and helium with a little bit of other things like carbon, nitrogen, and oxygen. In fact, oxygen is the third most abundant element in our universe. And so we think that if you combine oxygen with hydrogen, you get water, right? H2O. And so we expect there to be a lot of water. Not finding the water was a big puzzle from the Galileo mission. So the plan is to go back, find out what's inside Jupiter, and our ideas of how gas giants form, test our ideas, and go and see where the water is. So we have a spacecraft like this that was built in Lockheed Martin in South Denver. And you can see, I think you can see, can you see this from the back, or are these in the way? Pretty much see? No?
Yep.
Maybe have a stand if you need to. So this is a human. This spacecraft would not fit in this room. He would sort of poke out the corners. And so it's about 60 feet diameter. And the solar panels provide about 500 watts of power. And it spins every 30 seconds. So that's sort of like this. It's spinning, but it's fast enough that you can't just stare with a camera and take images that way. Now, it's great if you're measuring charged particles with JADE and JEDI and the magnetometer measuring the magnetic field, because we like to have a spinning spacecraft. It gives us stability and we get a lot of views. We have waves, which measures waves, radio and plasma waves. We have two spectrometers, GRAM and the UVS spectrometer, which measures the UV and infrared light. We have gravity science. I'll show you how that works using the antenna that communicates with Earth, and we can use that to measure the gravity of Jupiter. And then we have a microwave instrument, and I'll show you again how that works. That's for detecting water. And then we have a camera, and we stuck a little camera on because it's a NASA mission. You always have to have a camera. You're going to see some amazing pictures. Okay. So this is what we have. We launched it. The whole idea is to get up close to Jupiter. And so we have to fly underneath these radiation belts that are around Jupiter. So this is a problem, making measurements that is so close to the planet. You've got to avoid these radiation belts. So these are charged particles that are trapped in the magnetic field, and that will damage a spacecraft if we go through them. So we go from pole to pole in 2 hours. That's like going around the Earth at 5 times in 2 hours. So it's really moving very fast. And then the trouble is that because Jupiter is spinning, it's faster at the equator than the poles. And that oblateness of the planet means the orbits will evolve from 1 to 16 to 31. Down through, eventually going through the radiation belts. So that's the plan, what we're going to do. Same one. Oh, the only other point that actually was made here is we fly about 1,500 miles above the clouds. That's pretty close, moving pretty fast. Now, this is the idea. The earlier pictures of the interior of Jupiter have this core inside, a mixture of rock, metals, and water and ice and so on, onto which the hydrogen is formed to form another layer. And so the picture on the left is a sort of layered planet, which is the sort of textbook view. And on the right is what more current theorists are sort of arguing that when you have the high pressures at Jupiter that you have inside, deep inside Jupiter, then you will have the heavier elements will not form rocks and metals. They'll break up into different separate elements of silicon and iron and calcium and so on. Will dissolve in the hydrogen and get more mixed up. So is it the left or the right or something in between? Okay, so how do we measure the gravity? Well, what we do is we send a radio signal back to Earth with a particular frequency. And as the spacecraft moves past Jupiter, if Jupiter has a distorted distribution of mass inside, it'll make the orbit perturbed, and we can measure that perturbation of the orbit using the Doppler shift that's the shift in frequency of the signal going back to the Earth. So we measure that signal coming back to the Earth, we measure the small change in frequency of that radio signal, and that gives us a measure of the disturbance of that orbit, and that gives us the mass inside. Now that may seem like a very indirect way of measuring the mass inside, but we've done this at a lot of planets, including the Earth. We can do it pretty accurately, and we've shown that we can do this at Jupiter too. We also measure the magnetic field. That tells us about that deep interior as we fly through. And what we're trying to understand is what it's like inside. So as you go inside the planet, the pressure begins to increase. And you start off with fairly low pressures where hydrogen behaves like a molecule, where you have together protons and electrons bound together. So two protons together with electrons going around them in a molecule, tightly bound. But once the pressure increases and you go down, and you get down to 2.5 million bars, you start separating out the protons and the electrons, and they can move independently. So positive protons, negative electrons moving relative to each other, that means it's electrically conducting. You have charges can move around, and so you have a material that's deep inside Jupiter that's more like mercury or liquid iron that can flow and carry electrical currents, and that's where we think the magnetic field is generated. Now we've got this phrase, 2.5 million bars. What on earth does that mean? Well, let me explain to you what the pressure is like at the center of Jupiter. So, what's the pressure in this room? It's 1 bar, okay? We use that unit conveniently because that's us, we breathe it all the time. So that's the pressure in this room. And what is that pressure? Well, let's think about pressure. Pressure is force per area, okay? And the force through my feet is the force of gravity on my weight through my feet, okay? And the area is the area of my feet, so force per area. Now, what if I stand on 1 foot? What happens to the pressure? Up or down?
Goes up.
It goes up, right? Half the area, so doubles the pressure. Okay, so what's the pressure in this room? Well, you need to have not 1 person, but 5 people standing on my shoulders, and then the pressure through my feet is equivalent to 1 bar. Now, this is really hard for people to feel or appreciate because we're so used to that pressure, you don't think of having 5 people standing on your shoulders. And it's also uniform. But if actually you took a human and you put them out into space, they would explode. We haven't tried that yet. I think we should try it. I could think of a few people I wouldn't mind trying that. Didn't say that. Didn't say that. Thank you. Thank you. Okay, so, but we want to know about the pressure at the center of Jupiter. It's a much higher. It's in fact 100 million times the pressure in this room. So that instead of having humans, you need elephants. Not 1 elephant, but 1,000 elephants, all standing on top of each other, with the bottom elephant standing on 1 foot on a stiletto heel. Okay, so that's the pressure at the center of Jupiter, 100 million bars. And so you only have to go down to 2.5 million bars for the space transition to happen. So somewhere between 80% to 95% of the radius, and then you have this big volume of dynamo inside where you generate a magnetic field, a really strong magnetic field generated by Jupiter. Okay, so that's the deep inside, but we want to try and work out what's going on. We also want to know where the water is and what drives the winds and so on. And so we need to map out the heat coming from the inside and see how much of that heat is absorbed by material in the outer layers. So if we look at an infrared picture, you see the bright regions are looking deep inside between the clouds. The dark regions are the cold, high altitude clouds, the belts and the zones there. And then when we look at a pressure diagram going down, increased pressure, so 1 bar, 10, 100, 1,000 bars, we can measure only the top layers using infrared down through the ammonia clouds. If we want to know the amount of water, we want to go deeper, and we want to use microwaves. So you know that microwaves absorb water. That's how you heat up a cup of tea or some food in the microwave oven. You put that in, the microwaves are then absorbed by the water that's in your food. So if there's water in a layer here, maybe in different distributions inside the outer layers of Jupiter, then we map out the amount of microwaves coming out at 6 different wavelengths, and that allows us to map the microwaves inside Jupiter. Map the water that's absorbing those microwaves inside Jupiter. Now, previous flybys have always been at the equator. We've mapped out the magnetic field of Jupiter, which is huge, very strong magnetic field, extends a long way out, 100 times the size of Jupiter in this direction. We could fit all of the Earth's magnetosphere inside the planet Jupiter. So this is a vast region, and indeed we know that it extends all the way out beyond the orbit of Saturn, away from the Sun, because when Voyager 2 went by Saturn, we happened to be in the tail of the magnetosphere of Jupiter. So this is a vast volume extending a long way, like a comet away from the planet. And the source of this is the moon Io, which spews out a ton a second of material. So Io is this volcanic moon that is covered in volcanoes. It's the first of the 4 Galilean moons, Io, Europa, Ganymede, Callisto. And it is tidally heated so that there's no impacts on the surface. It's completely turned over. It's probably turned over several tens of times in the age of the solar system. These dark bits are lava. The white bits are sulfur dioxide frost, and the yellowy bits are sulfur. So this is a visible image taken by Galileo. This is an image taken by New Horizons, that spacecraft on its way to Pluto, got a gravity assist to Jupiter. You see Tvashtar erupting. This is a really high, big plume, like a geyser spewing out sulfur dioxide. And this material gets trapped in the magnetic field. It's ionized, then trapped in the magnetic field of Jupiter to make this big ionized donut around Jupiter. And extending out beyond Europa, Ganymede, and Callisto, it goes a long way out. And then the particles that are accelerated by these magnetic fields down the magnetic field to cause the aurora. And I'll show you some pictures of that in a bit. So we've been observing that for some time, and indeed Voyager flew past Io and measured that there's 1 million amps of electrical current that flows between Io and Jupiter. Okay, so there's a really strong electrodynamic interaction between Io and the planet, as well as Europa. And Ganymede. Ganymede's really special. Anybody know why Ganymede is such a special moon? What's so special about Ganymede? It's the largest moon, yeah. It also has a very special property that no other satellite has. Same size as Mercury, has a similar property to Mercury. It has its own magnetic field. Yeah. So it also is a magnetosphere within a magnetosphere. And it also has electrical currents that connected to the planet. We'll see the manifestations of that later. Okay, so this is a new Juno picture taken in the infrared with that Juno image. And you can see here, the infrared imager, you can see these hot spots. So these are all active volcanoes that are glowing and showing us the volcanoes all over here. Okay, so this ton a second of material coming volcanic gases fills up at this big magnetic field environment and drives in a million amp currents between the moon and the planet. Okay, so we see this with Hubble Space Telescope. We've been observing for some time. We see aurora. This is in the ultraviolet part of the spectrum. This is hydrogen gas glowing in the ultraviolet. Energetic electrons come in and bombard the atmosphere and make it glow. And we see this main aurora. I'll show you some more of that in a bit. But we also have these footprints, Europa, Ganymede, and Io over there. And if we look at a movie, you can see how the steady main auroral oval, the variable polar aurora, and we don't know why they're so variable. Is it like Earth, driven by the solar wind, or is it something else? And that's what Juno, flying over the poles, is there to measure. Here's Io with that million amp current driving strong aurora in the atmosphere of Jupiter, and then a little feebler one of Europa, a strong one of Ganymede. Okay. So the point of Juno is to fly over these polar regions, measure the aurora in the UV and the infrared and the visible light, measure the magnetic fields, the waves, the plasma waves, the electromagnetic waves, and measure the particles that bombard the atmosphere and cause the aurora. That's what we are doing. Okay, so time to go. I was allowed to go visit, and I had to dress up in the bunny suit to really make sure that the instruments kept very clean when they build the spacecraft. It took about a year and a half to build Juno. Since we're so close to Lockheed Martin, I wouldn't be surprised if there's anyone in the room who's involved in building Juno. Sometimes when I've come here to the clubs, there's been someone who came from Lockheed. Okay, so this took about 18 months to build. A lot of people worked really hard to make it work, put it all together. And solar panels that were tested, built, tested, attached to the spacecraft, then folded up. And the whole thing was shipped out to the Cape, put on top of an Atlas rocket, Atlas 5, with 5 solids underneath. Put a fairing on top, slap the stickers on, very important. Take a selfie, very important. And then we're ready for launch. And all went well, launched on the 5th of, launched on the 5th of August and set off. Didn't have enough umph to get out to Jupiter, so I had to come back, get a gravity assist to Earth, and head out to Jupiter. So as we approached, we were approaching on the dawn side. So we're looking at Jupiter from the sun, and we came in like this. And as we approached, we had a special opportunity to make a very special movie. And we were able to look at Jupiter and see something special. And this animation just points out that, you know, for billions of years since people crawled out of the caves, they were looking up at the sky and saw some bright objects move relative to the stars. Those are the planets. And of course, Galileo used his little telescope, one of the first people to look at Jupiter with a telescope, and what he saw were the moons, the Io, Europa, Ganymede, and Callisto. This is not a simulation. This is real. This is the view taken by Juno camera looking at Jupiter. So photons, sunlight left the sun 40 minutes ago, came in, reflected off Jupiter and the moons, and came into the eyeballs of the camera. And we were able to watch for several days, weeks in fact, because the orbital periods are 42 hours, 84 hours, and twice that, whatever, twice. Anyway, So Io, Europa, Ganymede, and Callisto are in these orbital residences. Io going around 4 times, so every 2 times Europa goes around, once Ganymede goes around. Now you can see as they go behind, they blink out, they go through the shadow. Can you see that? Right, isn't that cool? And then Callisto around that. So this is the first time we've had this view and made this movie. We've never had the opportunity to do it before. Of course, Galileo was looking from the Earth, and night after night, we was able to sketch where things were, but didn't get a continuous view of what was happening. And so this view, it's not as revolutionary as it was for Galileo, but really shows us for the first time these notions, which were so important in changing our view of the universe. Okay, so Juno is on its way, it's arriving, and is there making measurements. So we had an orbit insertion on the 4th of July. It was the 5th of July in Europe, but in California it was the 4th of July. But of course we were a bit nervous because we had to go close to those radiation belts. And they're kind of scary. And so we were worried.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, it's gravity. It's like a giant slingshot, slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon. It just so happens, deep inside this body, are the secrets we're after. Secrets about our early solar system. It's the biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation, the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about 1/3 of a rad. What we expect to see at Jupiter is about 20 million rads. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we're going to go in close, get the data, and get out. And the first time we go in, that's the most dangerous. We call it Jupiter orbit insertion. JOI.
Nothing's really certain about what's going to happen.
Okay, well, we had a lot of fun with that.
Suspense, did it make it? Did it make it?
I know, it didn't make it. So the point is, the guy who said it's a monster is the head of the mission. That's Scott Bolton, the PI of the mission. And the woman, she's in charge of the radiation belt studies. So, I mean, you know, it was, you could tell they live near Hollywood, kind of. But we were a bit worried. We were not sure what would happen when we fired those engines and went into orbit. We did survive, and orbit insertion went well. And then since then, we've actually had 16 flybys and gathered a lot of data, the last one being in October. And we're in 53-day orbit. So we do this 2 hours pole to pole, and then we go out and we send the data back, and then 53 days later come back again. Okay, so what are we finding? Let's talk a little bit about the magnetic field. To start with, the magnetic field is like Earth. It's sort of tilted by about 10 degrees from the spin axis, so it sort of wobbles every 10 degrees. But at Earth, the magnetic field comes out of the south pole into the north, and the Jupiter comes out of the north and into the south. Now, of course, the Earth's magnetic field flips every roughly 200,000 years, and we haven't seen any changes yet at Jupiter, but we've only been observing for about 60 years. We've got new measurements of the magnetic field, some hints of changes. As we get up close, we see differences compared with the magnetic field models. And what we see, if you look at the north and south, this map at the bottom shows you that the North Pole is a lot stronger than the south and much more irregular. And indeed, when we look at this model of the mapping of the magnetic field, we have an anomaly, a strong region of magnetic field, a weak magnetic field here, which is a bit like the South American anomaly that we have on Earth, where there's a lot of extra radiation belts and a lot of instruments have problems with the magnetic anomaly on the Earth. This is not a magnetic anomaly. This is where the fire breaks up. Okay. So what's going on inside? Let's talk about the interior. What we're seeing now is indeed it's not the simple layered structure that we thought that the textbooks have. What we're seeing is that it's fuzzier. There's a boundary where things are mixed up, and indeed a lot of that material, that iron and ice, that core around which the hydrogen formed the gas giant planet, is mixed in, and we think those heavier elements are now mixed in out to about 40% of the radius. So that's what we're finding so far with our first measurements. We're also measuring the evidence of helium raining out. Helium doesn't mix very well with hydrogen. It tends to separate the way, or vinegar separate in vinaigrette. And so the same sort of thing is happening here with the helium raining out. So we're getting some evidence, and certainly the boundaries seem to be a lot fuzzier than we thought. That's one of the main new results that we're getting. We're also mapping with the microwaves some sense of deep circulation going all the way down through below where the ammonia layer, the ammonia hydrosulfide, and then the water layer, and mixed in with the water layer is ammonia. So there's some turning over, which we don't quite understand. There seems to be an upward rising near the equator, and the question is, well, how does the circulation, deep circulation, work? And we're starting to make these measurements with the gravity and the microwave. If we look in the infrared, we have this amazing view of all the storms and these cyclones and belts and zones. Remember, light color means hot. We're looking deep down inside. Dark means cold, higher up. So this is what we get with the infrared camera. And then we have the visible camera. So remember, the visible camera we just sort of slapped on last minute, and we decided this was going to be an outreach camera. And so it's citizen science effort, and people could go in and vote originally. We've actually had to stop the voting because there isn't really, the orbit has changed a bit, and we're not able to make a lot of choices about how we observe. But you can download the images almost immediately. They're posted, which is within a day or so, and you can then explore with them. So this is the sort of images that, if you look in true color, as your eyes would see it, we were flying over. But the citizen scientists have had fun cranking up the contrast. And so this is not the real color, but it's really useful because you can now begin to see, when you get up close, the degree of turbulence that you're seeing here in this atmosphere. It was really amazing. Okay, so it's not the real what you'd see with your eye, but it really is the dynamics. And then what people are doing is they're doing artwork, which is fantastic, right? And then posting up their favorite pictures, which, you know, is fun. Right? You know, they own these pictures as much as anyone else. So this is a lot of fun. Go check it out. There's some amazing stuff up there. Okay, so other people are trying to do science. And so remember, we're on a spinning spacecraft. And so we can't stare at the planet and go click, 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 or make a movie because we're spinning every 30 seconds. And so we tend to get strips of the atmosphere and put those together. This is a polar view, And now we can see for the first time that there are these vortices around the pole, and we see a bluer color at the poles. So a similar sort of blue process that makes our blue sky, really scattering of molecules, blue light of sunlight being scattered. Whereas at the equator region, what we're seeing is this reddish pollution of UV light reacting with the gases to make reddish material. A bit like the red cloud, you know, Denver red cloud, right? I'm sure you don't have red clouds here in Colorado Springs. No. No pollution here, no pollution. Okay, so this is the multiple images put together, and you can see this amazing view now of the poles of Jupiter. This is actually two day sides sandwiched together. And you can see here now in the infrared, again, dark color means high and cold, bright color means hot and deep, but you can see these vortices very clearly in the infrared, and you can see 1, 2, 3, 4, 5 in the south around the central pole, and then 1, 2, 3, 4, 5, 6, 7, 8 in the north. Okay, so they're different north and south, and we're not really sure why or whether that means anything, but these have been persistent now. When we've looked, they've juggled around a bit and moved a bit, but basically this pattern has been the same for 16 flybys. The interesting thing is it's very different to that of Saturn. So if you look at Saturn, you have this hexagon at the pole. Right? Can you see that hexagon? Now, we've known this for a long time, since Voyager, but we're getting a better view with Cassini, and you can see this big vortex around the North Pole. And so the question is, why does Saturn have a hexagon and Jupiter have these 5 and 8 vortices north and south? Maybe it's related to the fact that the mass of Saturn is a third the mass of Jupiter, so they're just driving rather different atmospheric dynamics. It's not clear. So these are the sort of things we're looking at. This movie is a fairly recent, from the last phases of the Cassini mission, and you can see it's really kind of cool vortex with the hexagon around it. Okay. So similarly, from the polar regions, we have these polar hazes, and I really love this picture because it's sort of like a cape. You can imagine a nice woolly cape. But this is the polar hazes up here, and then the belts and zones going around. So this is putting together a whole bunch of pictures together from different flybys to give a sense of what it looks like. Okay, so now let's look at some of the atmospheric structures and just the amazing level of detail in the structure. Now, there are some of these vortices where you seem to have white in the center and dark on the outside. So that would suggest fresh material coming up, condensing to make these fresh white ammonia clouds, hanging around for a while and getting murky and polluted by the photochemical smog around the outside. But then there are other places where it's lighter on the outside and darker on the inside. And we haven't yet studied all of these and said, oh, there's a systematic behavior, one cyclones, the other's anticyclones. We haven't done that yet, but you can see there's a lot of these things all rather different here. This is a polar region, more blue, but again, when you crank up that contrast, you begin to see the level of turbulence in the atmosphere is amazing. Here's my favorite owly eyes. Yeah, you can see, which is kind of cool. You can see all the turbulence over there. Other times, this one is, they haven't increased the contrast as much. It's sort of very aesthetic. Make a lovely piece of wallpaper, wouldn't it? There's again, this is another one with a high contrast near the poles. And then these are some of the more recent ones with all sorts of, these aren't just simple hurricane storms. There's a lot of additional turbulence associated with these. But you'll begin to see these white clouds that seem to be fresh, as if they're sticking up above the environment. There's a bunch of these ones here. Again, this is a large dynamic region. And here is an interaction between different belts and zones with the turbulence in between. What are you seeing in this one? What do you see?
See a face.
Oh, over here?
Yeah.
Like the two eyes and the nose and the mouth, is that weird?
Yeah.
Oh, yeah, okay. Well, you'll see some other things too in a bit. You're going to see, you start seeing all sorts of things. So if you get a chance to come up to Boulder on the Ides of March, so 14th and 15th of March, I'm doing a planetarium show at Fisk Planetarium. And we take these images, we put them over the entire dome and swirl them around and play Pink Floyd and, you should come and have fun. Yeah, right. So this is perhaps really one of the best examples showing you these white fresh clouds that are coming up. We call these pop-up clouds. And I think this is sort of what we're seeing. So I took this picture flying back from the East Coast, and you can see these clouds sort of sticking up. And I think this is typical of what we're seeing in these fresh pop-up clouds. So these are not necessarily where the lightning is happening, but precursors to thunderstorms. So this is a sort of thing, again, looking sideways on the Earth, this idea of having clouds sticking up above the surrounding cloud deck. Now, we do measure lightning, and we do measure thunder using the plasma wave instrument and the microwave instrument. But the interesting thing is that Jupiter, the thunder and lightning seems to be in the poles, whereas at the Earth it tends to be more around the equator. So there's something very different going on in the dynamics of the atmosphere of Jupiter, where there seems to be a lot more convection happening in the polar regions rather than the equatorial regions. These are just some more recent ones showing, again, really cool turbulent eddy there. This is in the equatorial region, a very turbulent band. Again, where we've wound up this is a developing storm here. This one I think was called, this is from the recent PJ16 in October, and I think they called this the Dragon Head. I'm not quite sure. You see a dragon? Yeah. Yeah. Okay. And then there's this one. Have you seen this? See the dolphin? Isn't that cool? This was the last one.
It's bigger than the Earth. It's scary.
It is bigger than the Earth. In fact, I think it's like 2 Earths, so it's really big. And it's obviously it's quite old clouds because it's dark, right? It's accumulated that brown gunky material, which we don't know what it is. So this is the more recent pictures that we've got. Really incredible detailed structure that we're seeing with this camera. So here's the Great Red Spot. Let's talk about this. Voyager saw this, and these colors exaggerated. We didn't have very good normalization of a coloring scheme back then. But you can see it was the size of 2 Earths at the time, turning around over many days. What we see now is, and we've been observing from the ground, maybe you guys have been using your telescopes, amazing telescopes that you have, looking at Jupiter, and you may have noticed that the Great Red Spot's got rounder, smaller, shrunk, and it's now about 1.5 times the size of the Earth. You see these beautiful turbulence in the eddies around the sides with the Juno data, and really we don't know what's happening. It's clear that the stuff in the center has been around for a long time, so it's been isolated. Remember, this has been around for around 400 years, and so it's accumulated a lot of this gunky stuff in the center. But the question is it going to keep shrinking? It will disappear about 2050 at the current rate of shrinking, or will it break up? Will it just get bigger again? We just don't know. And why is the one in the southern hemisphere, none in the northern hemisphere? Why, we don't know. Okay. So this is something to watch. We're actually going to fly right over in a couple of orbits, measure the gravity, measure the microwaves in very detail of the Great Red Spot. So this is, again, one of the more recent pictures that the amateur community, the citizen scientists have put together. But that's not bad for public outreach, eh? Not bad. Okay. So let me just show you a little bit of what we're learning now. If we look at the interior, we're not able to stare and measure the clouds like this. This is actually from the Cassini, but we are able to probe using the gravity in the microwaves down to as much as 3,000 kilometers, telling us that this is a really deep, still shallow compared to the size of Jupiter, but a fairly deep convection system, whereas up near the poles, there doesn't seem to be as strong a belt and zone system. Now remember, Jupiter spins every 10 hours, and it's 318 times the mass of the Earth, so that's a lot of angular momentum in that planet, okay? And so it drives these very strong east-west winds, particularly at the equator. And so it could be that you're getting these strong winds and the turbulence associated with those wind shears near the equator, and up near the poles, you're getting more of the thunderstorm type convection, which we tend to have at Earth more near the equator. Now remember, the big difference is that the heating for our atmospheric, driving our atmospheric weather system is the sun, right? It heats the equator up more than the poles, drives convection systems in the Earth's atmosphere. For Jupiter, Jupiter radiates 2.5 times more internal heat than it receives from the sun. And a lot of that internal heat comes out near the poles, where the rotation is less, and the equator, the wind shears just rotate and smear everything out. So we're sort of learning a difference in these wind systems, dynamics of these different, how this is being driven by a very different situation on Jupiter than we have at the Earth. So we're also learning about the aurora. We have these very dynamic aurora. Again, you can see where those million amp currents from Io connect to the planet. Again, with the GRM and the infrared, we're seeing all sorts of structure. They've got some new, there's actually, I saw a couple of weeks ago, an amazing visible picture taken with the camera that was supposed to be used for getting the stability of the camera that we use for measuring the stars to get the stability of the magnetometer boom. Okay, so we use these sensors to take pictures as well as to do the background measurements. And it has a picture of the aurora that is sort of a small little picture, but it's got all this structure. And so like at Earth, when we zoom in, for the Earth, we tend to do it by looking up and then having to integrate to get a bigger picture. But for Jupiter, we've only just been able to zoom in and see all that detailed structure in the aurora. And then, of course, we're flying over and measuring the structure in the particles and fields as they fly over. Now, it turns out that on April 1st last year, we flew through the flux tube and actually went through here, through this million amp current, and we were able to measure the 20-second burst of magnetic and electric fields here with the waves instrument, just as strong burst. We had very energetic particles, and electron center saturated as it flew past through this flux tube. And then when we look down on the aurora with the infrared camera, this is where Io, the main spot, and seems to be what looks like turbulence behind Io in the flow of plasma going past the moon, producing this disturbance behind and stretching a lot of the way around the planet. So we're learning all these new things about the aurora by flying through the regions over the poles, looking at the aurora, looking at the particles, measuring the fields. We're looking at the clouds. We're looking at the amount of water using microwaves. We're using gravity to get the distribution of mass inside. And we're measuring the magnetic field with the magnetometer. And the first thing we know is this is wrong. It's not layered like this. It's much fuzzier inside. And we need a new cartoon that shows less structure and a more fuzzy interior. So thank you very much. Bring up the lights, but I'm going to leave this running, is this gonna work? Do we have like half lights? Is there any way?
No.
Is that all or nothing? Oh, well. Anyway, there's a movie that'll keep running, and if you want, you can turn the lights out. But maybe there's some questions. If people have questions, yeah.
Since you mentioned that we all know by observing and imaging that the great red spot has become smaller, but the Enigma seems to be the opposite with its color intensity. It seems to have faded rather than concentrated. Is there any idea why?
So you're saying that it's less red? Is that what you're observing with your telescopes?
Well,
Or
not
are
just
you?
mine. Many friends who just take
Okay.
planetary images have
Right.
noticed a great diminishing
Oh,
in
really?
the
In
color
the redness?
intensity.
Okay. The reason why I hesitated is that if you go on those Voyager images, they had the color balance completely wrong, and there was issues there. So I now know people are much more careful with the photometry to try and get the color balance right. And that's interesting that you're saying that, because I didn't know that that's what people were observing. My suspicion is that there could well be some ammonia haze over the top, cloud haze over the top. We should be able to see that when we fly by. We get this really close up in a couple of orbits. But that's a good point.
Maybe they can make a comparison of previous flyby.
Right.
Years back.
Compare
to a
them.
more recent.
Yeah. Yeah, no, the Cassini, so Carolyn Porco, you probably know, is the head of the imaging team on Cassini, was originally lived in Boulder. She was very careful in getting the color balance with the Cassini instrument. And I think we've been trying to do that color balance again with Juno. So important to compare and see. Yeah, that's a good point. Okay. Yeah, something to watch for. Yeah.
Just a follow-on comment from personal observation.
Yes.
When I was a 12-year-old kid, my first telescope was a 6-inch reflector.
Yeah.
The red spot on Jupiter was so obvious.
Yeah.
It was very,
Jumped out.
It was very there
Yeah.
all the time when it was on the.
Yeah.
Now it's very difficult to see in
Yeah.
8-inch or larger scope.
Yeah. So what do you think? It's going to come back? Who knows? Keep observing. Yeah.
What is your, the end of the mission, I mean, it's a certain number of orbits.
Okay.
I mean, what's the
What's the end of the mission? Yeah, right. And then I'm going to come back to you back there, so I haven't forgotten you. We're in these 53-day orbits, and we were originally going to go into short ones. Actually, we were really relieved we're not in the short ones. It's nice to have that break between the flybys. And so we planned originally, remember that we put in a bid, this team put in a bid to do this mission to NASA, and they said, okay, here's the money to do it. And we built it and so on and put it together. Then when it was extended, we had to have a little bit more money to keep us going. And so we think we can last 30 orbits and everything will be good. Now, what will happen is when we get, at some point, we're going to have to see how we're doing with the instruments. Are they surviving their radiation belts? And then if they're doing well, we go back to NASA and the taxpayers and say, please, can we have a little bit more money to keep going? Okay, so we'll have to see. The problem is the radiation belts begin to get nasty later in the mission, not earlier. So it's going to be difficult to judge that one.
more of that than fuel limitations?
Yes, so it's very much the radiation is likely to be the problem. So we may keep it going for a bit longer, but at some point there are likely to be issues with the instruments. Okay, so what is the most important thing that we don't do with a Juno spacecraft that came from Earth?
Callisto.
Callisto is fine. You don't care about Callisto. Europa. Io, we don't care about Io. I don't think there's any life on Io.
But is there very
But Europa could be, right? Underneath that ice layer, there could well be life in that ocean. And we don't want to bring bugs from Earth. That would be like kudzu, right? And cane toads and all of those things where we messed up our environment by bringing life from one place to another that then went rampant. So we don't want to do that. What we're going to do is probably send it into Jupiter. So we'll make an assessment spring of 2020 and say, can we keep going for a bit more? Or we say, oh, half the instruments are decaying, we have all sorts of problems. And we say, okay, enough. So we'll see. Yeah.
You
Oh,
had,
wait a minute.
you had indicated that charge area where all
Right.
those particles are collecting were probably a result of volcanoes and iron.
Originally, yes.
Originally, okay. Well, can you,
How do they-
you know, why would that be that charge?
Why did it be that? Okay, so the stuff that comes out of the Earth's atmosphere is mostly sulfur dioxide. It gets broken up into sulfur and oxygen and ionized to make sulfur ions and oxygen ions and electrons. Equal numbers of positive and charge. Plasmas tend to be equal in quantities of positive and negative charge. So those particles are trapped in the magnetic field. They rotate every 10 hours around Jupiter with that magnetic field. And then they spin up and down along the magnetic field. They spin around the magnetic field and they bounce back and forth, just like the Earth's radiation belts of our Newton belts at Earth. Now, what happens though is those particles at Io, which is at 6 Jupiter radii, actually move out because there's more of them in about 6 and they go out, spread out. And as they go out, they actually gain more energy from the rotation of the planet. So you would think if something's spinning and it goes out, it would slow down, right? Conservation of angular momentum, thinking of the skater, right? Putting the arms out slows down. But those charged particles out here are coupled to the spinning planet by the magnetic field. And so the magnetic field couples them to the spinning planet, the ionosphere, that keeps them spinning and adds momentum to that material, that disk of particles out here. So as the material goes away from Io, it gains energy and gets more and more energetic, the electrons and the ions. And then at some point, they get scattered into the atmosphere by waves, or the coupling is at some point gets to be difficult for Jupiter to maintain that coupling, and so you drive electrical currents, which are carried by electrons moving along the magnetic field. And it's those electrons that cause the aurora. Okay. So, but we've just talked at this point about stuff coming from Io going outwards and gaining energy as it goes out. Now, if you think of these as flux tubes, magnetic flux tubes, coupled to the planet, right? They actually switch around as it goes out, okay? So for as stuff, the full flux tubes with sulfur dioxide material, sulfur and oxygen ions, and electrons goes out, there's emptier flux tubes coming from the outside in, because you're switching these around, you're swapping them, interchanging these flux tubes. So you have flux tubes that were out here coming in. And as they come in, they're going into stronger field regions and gaining more energy. So the plasma seems to gain energy as it goes out, tapping the rotation of the planet, and then they come back in again, tapping the magnetic energy of the planet. So by the time they've gone from Io all the way out to the outer magnetosphere and come back in again, by the time they get in close to Jupiter, they're really energetic. And we're talking 10 MeV, mega electron volt particles. And so that is that high radiation environment close to Jupiter.
Molecules or just ions?
Those are ions and electrons, just ions. In fact, most of them in the inner region are protons, some sulfur and oxygen. Yeah, ions deep inside. In fact, Juno has detected new radiation belts associated with million electron volt ions and electrons deep inside. So this is why it's so dangerous, because these are really high energy, and they've gained it twice, once going out, tapping the rotation, and once again coming further accelerated, coming back in due to into the higher magnetic field region. So yeah, it's really very accelerate. So Jupiter's magnetic field is a really high accelerator, if you like. It's like a particle accelerator. Yeah. Okay, yes.
When is the next close approach?
The next close approach is PJ 17, and it is 53 days after October 16. I think that's right. You know, I chair the science planning working group. I should know that number on the top of my head.
Is it December 21st, 2018?
Which one?
December 21st?
It is December 21st. Thank you.
I just
I
guessed
knew
that.
it was just before the Christmas holidays. So yeah, December 21st, which I think is a Friday. Yeah. So the new pictures should be out in time for Christmas. Should be cool. Yeah. So that's PJ 17. Yeah. Yeah. Right. Okay. Any other questions?
On the
We'll come back to you and then.
On the ionization,
Right.
is it possible to get that effect on spectroscopy at all?
Yes. Okay. So this is really cool, and this is what I've been working on for a long time, is to look at the sulfur and oxygen ions that come from Io. They actually glow in the UV, and we have been observing them with various satellites like Hubble, but there's a Japanese satellite called the Hisaki satellite that has been observing them all the time with Juno, and we have beautiful images and spectroscopic observations that tells us the amount of the different ionization states of sulfur and oxygen. But there is also visible lines of sulfur, single ionized sulfur, and that's in fact how it was first detected back in the 70s. So it might be possible that if you have, it's quite possible that you could probably get a filter of some kind that you could use with your own, if you've got enough observing area and a good enough filter. I don't know whether they're available, but I suspect they are available to purchase, to put on your telescope. The other thing is sodium. There's a very strong sodium line, right? And neutral sodium, Io also spews out neutral sodium. This is the first thing that was detected. I don't remember the lines on the top of my head. I actually know the UV ones better than the visible ones, but you can go, I think that can be observed with a modest telescope, the sodium near Io. Yeah. Yes.
So we actually have a question from a group in Liverpool. Online. It says
It's 3 o'clock in the morning.
they're dedicated, for sure. Has Juno been able to detect any zones around Jupiter or Europa where the radiation may be weak enough for a human colony?
Oh. No. I don't know what the you go and live on Callisto, okay, the boring one that isn't in orbital resonance, that's just a lump of ice. But okay, I will say my piece. There's nothing that humans can do in space that robots can't do cheaper, more efficiently, and better, except tourism. And I don't think the taxpayer should be paying for tourism. So, I mean, the answer is no. This place is brutal. To send humans to the Jovian system is bonkers, really. And so, no. Send robots. They do a lot of cool stuff.
Just run real quickly, you can answer. Is there still, or are there plans to actually put together like a nuclear ship torpedo submarine and send it to Europa?
Okay, good. I'm glad you asked that question. So the next mission is indeed a mission to Europa, the Europa Clipper. And I think the current plan is a launch date on the order of 2023. It was 22, but I think it's moved to 23. The real problem is what to launch it on. And does it go on the SLS, which is not launched yet? Do you wait 1, 2, 3 successful? What if there's a not successful? What do you do? This is going to be a $4 billion mission. At what point do you put it on the launch vehicle? Alternatively, what about the private vehicles? What about a full condition? Yeah, whatever. So that is a big question. Yes, you need a big vehicle. So that's a question, is how to launch it. But there is a plan. They're working on building the spacecraft, putting it together, and it is actually solar powered. For Jupiter, you can use solar power. I actually think it's a bit crazy to use solar panels for this because they're going to try and stabilize it so they can use cameras and all sorts of stuff. Difficult mission, I think, to do. But after a long period, after the Cold War, of not building radioisotope thermoelectric generators, RTGs, which have powered that spacecraft and Cassini and Voyager and Ulysses and Galileo and Pioneer and just about everyone you can think of, certainly the outer solar system. You cannot go beyond Jupiter with solar panels, I don't think. They have started to build the put together the plutonium-238, which is not the bomb plutonium. It's the other one, or one of the other ones. And they build it in a reactor and put it together, concentrate it to make this plutonium that decays with a 80-year half-life. That makes heat. You turn that heat into electricity to power the spacecraft. And that's what we've been doing since the earliest days. And we've just started to rebuild that facility to do it again. And they will continue with a bit of luck. Yeah, we need that for Uranus and Neptune, which is the place we have to go next. We must go back to Uranus. Okay, yeah?
So that was sort of one of the questions I had was power budget that you have, because 500 watts is about what you have on stuff.
Yeah.
So if you would have had 200 or 300 more watts of power, what would you have wanted to see on board?
Well, we do actually have to turn off a lot of the instruments and turn them back on again to conserve power, and particularly the communication is the big deal. We had to really fight over who gets the bits to come back to the ground. So if we had a bit more power, we would have a bigger antenna and more powerful antenna. Remember that spacecraft there, the New Horizons spacecraft, 6-foot antenna, communicating from 33 times the distance between the Earth and the Sun with a 15-watt antenna. That's a refrigerator light bulb. Okay? To the deep space one. If you the DS1, the deep space network, if we could put more power on these spacecraft, we could send back more data. It still takes that travel time, but you could send more. I think New Horizons, I think, is 3 kilobits per second. That's a typical phone. 50 megabits, right? I mean, so this is tiny data rate. It took 18 months to get all the pictures back. So that's what we need to do with more power. Yeah. There was one other question at the back there. Yeah.
I knew that I knew Jupiter on my radio.
Yes.
Is there a schedule that you can go by, or?
Yes. So you can listen to radio emissions from Jupiter. That was how it was first detected back in 1954, almost to the day around the time I was born. Interestingly enough. But actually, it's been observed for a long time. And the EO triggering radio emission has been observed since the 60s. Boulder, there was a big group up there was observing. We tried to observe it at the university. I actually bought a little radio antenna. I got some students to do it. There's too much noise in town. So you would have to go out. You live out of town, away from radio noise. Well, you may just hear all of the TV and the people and everything. You may not be able to. But there is a thing called Radio Jove. Go online, Radio Jove, okay? And there's a whole community of people who listen and do all this sort of stuff. And the schedule and everything is all there. So go for it, but you may have to find a friend who has a ranch. Or go, hey, how about going down to Rocky Mountain Source there? Yeah, I bet you that's radio quiet. Take your system down there and try it out. That'd be cool. And if you get that to work, let me know, please. I would love to come here. Yeah. Okay, last question. Sorry.
No.
Okay.
we have to
Good.
stop.
You got all the stuff.
Right. If there's anybody else that has any other questions for Fran, we're gonna take a 10-minute break here in a couple minutes, and I'm sure she'll be happy to answer. Normally, Fran, what I do is I present the highly coveted and collectible Star Stare Colorado Springs mug. She's already found it, so. Awesome. One other thing, for those of you who are new here or haven't been around much, Fran and her team of colleagues has been supporting our club for years. She has done presentations at Rocky Mountain Star Stare last year. You have other colleagues that have done that. When I was vice president back in 2007, there was folks that came up from UC Boulder. So thank you for your continued support, for coming here and doing what you do.
Great.
We really appreciate it.
It's a great pleasure. Thank you very much.
All right, so what we're going to do is we're going to take a 10-minute break. We'll be back here at 8:05 with continuing on our program.
Oh, yeah, yeah.
It's good seeing you.
Great, yeah, good to see you. I'll have to think about organizing stuff studies, see, find out what the guys are.
I didn't go to this year. I went to.
I did.
I was at the Society for Astronomical Sciences convention.
Okie dokie. All right, we're going to go ahead and get started here. Outreach team. We have a big day tomorrow. We have a Space Foundation Star Party.
Hurrah.
800 some folks showing up. So anybody that can make that, please get a hold of Dave. Dave will talk about that at the end with his outreach report at the end of the meeting. Second of all, remember, send George or me an email regarding the Christmas party. If you're planning on attending, how many adults, children, and what you're going to bring, and then if you're going to participate in the White Elephant, that would be greatly appreciated. Travis, can you come on up, please? Sure. For those of you who don't know Travis Shank, he has been helping us out all year long. He is our gatekeeper. He helps get our room set up here, making sure that everything is operational. He stayed late a couple times. We've had a couple late meetings this year. So the Colorado Springs Astronomical Society would like to say thank you, and we have a little gift for you.
Oh, thank you very much.
Thank you very much. Appreciate it.
The Discovery Center really appreciates having you guys come and visit us. We feel that it's a natural partnership to be talking about space and having astronomical meetings here as well. And we want to continue this into the future because space is there for everybody. And we believe that when you invest in space today, you're investing in a better future. And what you guys do in your outreach and even your personal passion continues to inspire people all around the world. When I watch kids look into your telescopes and go, wow, that is inspiring the future, and that's making our planet a better place by looking at space. So thank you all for coming here regularly and being a part of the Discovery Center.
Thank you, Travis. Okay, we're going to go ahead and move directly into observing reports. Does anybody have an observing report? Scott, do you have?
Yes, I do.
Do you have one?
Well, it's not. It's more of a trip report.
Okay.
Kind of related to observing. So you go ahead and get the lights up front. And I said I'll be quick. So as soon as you get it up, Steve, let me know. I attended 2 weeks ago the 2018 annual meeting for the American Association of Variable Star Observers. So here I am circled here in the group photo. We also had another member of our club, Cliff Kotnick, was also in attendance, shown here. Okay, next slide.
100 years.
All right, part of the highlight of being down in Flagstaff of the Lowell Observatory hosted the meeting, and so as part of that, we got to kind of get a special tour. The 24-inch Clark refractor, the building on the left, a little bit more of a close-up of the dome on the right, and then on our observing evening viewing for our group, that's just the lower end of the Clark refractor. I couldn't fit it into a single field of view, so it gives you an idea of how large it is. Here's the our host compared to the size of the scope. Next slide. Just a little historical. So, we've all recognized this picture of Percival Lowell sitting at the chair on this platform looking through the telescope. Inside the observatory is the same platform and the very same chair that he sat in. So kind of a neat historical context. Next slide. And then we also took a look at the 16-inch Bowler and Chivens reflector. This will be the smaller cousin of the one that's been donated to us by the Air Force Academy. So here it is here. Percival Lowell is also resident at the observatory. He's not alive anymore, but he's inside his own mausoleum, which is just a few stone throws away from the observatory. Next slide. And then this is the last one. We also got to see the Pluto Discovery Telescope. Dome is on the left. The 13-inch astrograph view on the right, and then I also just decided to put in the discovery photo of Pluto, showing Pluto here on January 23rd, 1930, and then just below these two stars down here on January 29th. So good meeting, and probably do it again next year. That's it.
Anybody else have any observing reports? Fred.
A good comparison as well as observing. At the last meeting, I mentioned I had guests, and one of the things we looked at was Mars. And we all know about seeing conditions, and last night was a perfect comparison when my brother and his wife were visiting from California, and we went out there, and it looked like it could have been a very good night. But with all the melting precipitation that we had recently, humidity level was quite high, and trying to see the polar regions compared to the last meeting or prior to the last meeting was very challenged, because it was like having a huge haze over Mars. You could almost make out a polar region, but it was nothing compared to a month.
Anybody else? All right, moving on. Vince, are you ready?
I'll dim the lights again real quick, and we'll do an abbreviated what's up. Next slide. So lunar information, I think we could nickname this one the K9 new moon, because there's Canis Major and Puppis are beginning to come into view. We've got 2 months here, and so you'll see January dates as well. But the Native Americans called the December full moon the cold moon, and then the January one the wolf moon. So actually kind of goes well with all the K9 theme there. And then maybe we could name the new moons, the K9 new moon and the winter Milky Way new moon. I don't know, just suggestions. Next. So we'll just look east for the next couple of new moons, December 7th, January 5th, and then January 28th, which is our next meeting, which is the last quarter now. So yeah, and we can see that things are starting to turn into sort of the winter. This is the wrong background. Next slide. Start to the right. So yeah, Orion should. If this is at dusk, it would be a lot higher just a couple hours later when viewing will be good. Next slide. A little more reasonable. So Gemini's nice and high, and this is in January. So next slide. I tried to do this inverted color for high contrast. Again, this is looking zenith in December and the new moon. We can see that Gemini twins, Regia, Perseus, Triangulum are all good targets. There are a couple of DSOs that are worth looking at in those constellations. I'll highlight a few in Orion, which is down a little bit lower than up in Zenith. Next slide. Again, Zenith a month later, things haven't changed much. You can see Leo is starting to move into view, and we're starting to get into galaxy season there towards the end of winter. Next slide. So we have Orion here, and it's comically large with these scales to try to make it visible. So it's kind of hard to see, but of course this is Sirius and Orion's belt. But if you go to the next, I've highlighted a couple of things that are worth looking at. Here's what's up. So over here is actually a really nice object that makes a little triangle with Puppis here and Sirius. And if you look there, there's M46, and I've got a slide on that one. And then if you look here, of course, there's M42, and that is like one of our showpiece objects that even from light polluted skies shows very well. Down here is Heinz Crimson Star, and if you look beneath Orion's foot here, Rigel, we've got a couple of this little trapezoid here and there. And this makes almost a triangle, and that is our Horus. It's Heinz Crimson Star, very beautiful carbon star. And then way off to the right here is actually Omicron 2 Eridani, which is a triple star system where you can see a white dwarf and a brown dwarf and a regular star, which is kind of cool. Next slide. So I pulled these from the internet. NASA produced M42, just spectacular, right? This is a reflection nebula. There are new stars being formed in the center, lighting it up. Next slide. So again, an exploded view of where to find these next ones. You've got M47, which you can actually see from a dark sky like Starry Meadows with your naked eye. It's an open cluster. And right next to the patch is M46. So next slide. I didn't take this. This was an astronomy picture of the day. But it shows this beautiful open cluster, which actually looks a lot more dense. It looks like something out of the summer Milky Way in Sagittarius or Ophiuchus. And you've got this neat little planetary nebula, which of course is the outer layers of a star being puffed away and lit up like a fluorescent light bulb. So next slide. there's that star again exploded. Burnham's handbook says that the center star has a temperature of about 45,000 Kelvin, is one of the hottest stars observed. And that planetary nebula is not a part of the system. The system is measured about 5,000 light years. This planetary nebula is more like 3,000 light years. From a dark sky like Starry Meadows, you need about a 6-inch scope, and this will show up well. It'll take an O3 filter, really nice. You won't see the center star, you'll see the planetary. And then a couple of stars for a change, that's what's up. You know, a lot of people think we look at stars. Well, here's some stars worth looking at. So that 40 Eridani, or Omicron 2, is actually naked eye visible, bright enough from a dark sky site. And then if you look at it, you can actually see multiple stars there. And one of them is a brown dwarf, which is a cooling off white dwarf. It's generally pretty hard to see those. Once they get too cool, you can't see them at all. So that's pretty cool. And then Heinz Crimson Star, quote, like a drop of blood on a black velvet background. This is a beautiful smoky star. It's actually cool enough that they've seen the spectrum of water in its atmosphere, which kind of blows my mind. In a star, there is water. Actually, when I go and view it, it takes me a couple of seconds for my eyes to see it, even when it's in the center of the field. So if you're having trouble finding it, and it is fading right now, it gets even more pretty as it gets dimmer, even though it's harder to find. It's about 9th magnitude. It'll drop to 12th at its lowest, and then return. It's got about a 300-day period. Next slide. So planets, most of them are in the dawn and not worth looking at. There is one nice little arc that'll show up. I think I had another slide for that, but on the 11th, Spica and then all 3 of the inferior planets will be making a nice little arc right before dawn. Saturn's not worth looking at, though. It's way too close to the horizon and close to the glare of the sun. Mars is still our best bet for looking at targets. It's actually running against sunset and trying to stay up in a nice position. So that was it. Thanks, guys.
Thank you. Okay, we're going to move into committee reports. First one, Rocky Mountain Star Stare. Tom, do you have any updates for the membership?
Only say that we do have a speaker for Saturday night, and Robert Zubin. He's the guy that started the Mars Society. He's up in Denver. He's published, I don't know, a dozen or more books on the subject. If you ever saw the movie, you probably did, the movie The Martian, where we got the guy stranded on Mars. That whole scenario was basically Robert Zubrin's scenario. That's his vision of how we would put people on Mars and bring them back. He's going to be speaking Saturday night at
Perfect. Bruce, long-term planning?
Yes, we're looking to the long term for that. No, we got a group putting together both a white paper for presentation with the Air Force Academy telescope, and we're also doing some initial scouting of sites for probability of is the site suitable before we go out and actually proceed with getting it coordinated to see if it's consideration. We're bringing that all together, meeting in about 2 more weekends. I think I put it on the schedule. I probably didn't, knowing the way my brain's been going lately. But we're getting there. Moving forward.
All right. Is there an update for Starry Meadows?
We have power there on site officially. It's not connected to the building yet. Next month, we're supposed to get with the local to make a trench, and then shortly after that, put the power in. So we're very close to the end of the tunnel. Obviously, I'll be stepping well. We talked about that already. We got Barry taking over, so we'll kind of gradually blend things, but everything is good.
All right.
So okay.
Perfect. Astrophotography group.
7 nights from tonight, next Tuesday, we'll be meeting at my home. The topic for next week is, for a larger group, is dealing with software, not just capture software, but also some processing software, and we'll talk about that. For the new beginner's imaging group, which meets 2 nights later at Barry's house, we're actually going to be discussing things about some basic equipment, things to get, what things are good to have, what things you may not need. And then we have an outline which will carry on actually all the way through September. The whole idea is that you can have your equipment, see how it's kind of done, and actually do it. So about half of that night, those nights are involved with you, either with your equipment or somebody else is learning how to do it. So whether it's doing star trails, capturing Milky Way, or other every night's a little bit different. If you are interested at all, please make sure you get me your contact information, your email, so I could read it again, and the name. Thank you.
Right. Thank you very much. All right, moving on. Outreach.
All right. Hey, first I want to recognize that we do a monthly radio talk show, and that's podcast KRCC Radio. You probably heard about it. We've been going. We're on 4 years now that they've been giving these talks every Monday. They've got
9 a.m. and 9 p.m.
Let's say it again.
Every Monday morning at 9 a.m. and 9 p.m. KRCC.org has podcast history. You can go back and listen to Al and myself and various other people's ranting and raving.
You can subscribe on iTunes and Google Play or whatever. It's great stuff. So what we got, first of all, thanks a lot for everybody that's helped out with doing outreach. Friday night, I got to tell you, it was only a couple of us out there. I know that people had family stuff going on. That's more important. Got to go get that done. But Friday, Black Friday's hike at Garden of the Gods, we had 3,000 people walk by our telescopes and look at the moon and look at stars and stuff. About a third of those actually stopped because we had long lines behind our telescopes. So, but it was awesome. It was really awesome. We enjoyed it. And Jim Urim was out there. Fred was out there. Or Ralph Reed. I'm sorry. I don't know why I keep calling you Fred there, Ralph. But we were out there, and the people really appreciated it. Had lots of questions about, hey, I want to buy a telescope. How much does this one cost? So I was trying to make some money, but I didn't succeed. But we had a good time. What we got coming up is, first of all, we got fluorescent fossil. Oh, well, of course, tomorrow, we got to be here tomorrow so that we can help the Space Foundation. They're expecting about, as they said, about 800 people. So let's get out here and support that if we can. We'll be able to dictate where we're going to be. We're going to be right outside the front of the building here. We get those lights outside turned off so that we can see stuff. Fluorescent fossil beds is on the 7th of December. Then just real quickly, let that come up. I've got Girl Scouts on what I'm going to do there. This one's kind of an interesting one. I screwed up. I scheduled something for them in August, but told them October. And so October came around and they called me on the phone. They said, we're out here at Garden of the Gods. Where are you? And I felt bad. And I went and I was like, there's no way I could have, messed that up. Yeah, I did. So we rescheduled it. What we're going to do is it's a Sunday. Well, I got to place it Library 21C, Pikes Peak Library District. We're going to be indoors for an hour and work Girl Scout activities. If you want to come help me do that, it's stuff like making the planispheres, and show them how planispheres work, and making a pocket solar system. So those indoor activities. Then we'll go outside and it'll be just getting dark, and we'll set up the telescope for them to look at the moon, and just a couple little activities. Well, Library 21C, if you can help me with that, I'd love to have you. I don't think I need any help for the one on the 11th, 6:30 p.m. at Banning Lewis Preparatory Academy, but you're welcome to come out and help. It's only for an hour, but we got some kids that want to look at the stars that night as well. Then on the 15th, we're doing some kind of different stuff, just trying it out, seeing what works. This one on the 15th, this is a Callahan Country Christmas, the second annual, Festival of Lights display. We're going to be out there with our telescopes at a Festival of Lights, right? Well, the good news is on the 15th of December, it's a half moon. So we'll have the moon to look at. So we're going to do, hey, people in Los Angeles show the moon to people walking on the sidewalks in downtown LA. I think we can show some people some views of the moon, you know, as they walk by, you know, to see the pretty lights, and think about come to a star party. Hey, think about joining a great purchase as become a member of the Colorado Springs Astronomical Society for a donation of $30. So, what's that?
Do we know where we're going to be set?
Well, it's El Paso County Fairgrounds, but where specifically we're going to be at, I'll know in the next week or so. Just to wrap it up, we got the Garden of the Gods solstice hike. So I've got Bruce is still good for that, right? So he's going to take everybody out on a hike.
He's going to bring you back.
And I hope they come back. That's a great hike, and hopefully we'll get one other people like Al maybe. Motivated, all right. And then we got one more CS Astro and the Dinosaurs. That's at Rocky Mountain Dinosaur Resource Center up in Woodland Park. In January, real quick, because we're not going to have a meeting real quick in January, we're going to be at Florissant Fossil Beds once again, beginning in January. And then the only thing else that I have on the schedule is we have a lunar eclipse coming up on the 19th or the 20th of January. We're going to be at Garden of the Gods from 7 to 11 p.m. I'm actually expecting maybe 1,000 people, depending on how much advertising that goes out there, but I'm expecting a lot of people. I think this is going to be an absolutely fabulous event. We've been talking about, hey, you thought that this was cool looking through our telescopes as you walk by on a hike. Wait till you come to a star party and see the real thing, right? When we have more telescopes out there. Well, we need more telescopes out there. So if you guys could help us out, you don't have to, you know, come to an outreach to see a lunar eclipse. Anybody can look out their backyard, but it's really cool to look through a big telescope at that, you know, lunar eclipse moon with the stars in the background. So that one, I'm really excited about that. I think we'll have a lot of people, we'll have a lot of outreach, and hopefully we can reach out in our press to the meteorologists and the other news people and get the news media out as part of that event and bringing that on. So that's what we've got coming up for outreach. I know it's winter time, but you know, people still want to look at the stars. We got cool stuff to see in the winter that we don't see in the summer. So good chance to come out and see some of that. If you can help us out, we really appreciate it. So thank you. That's all I have.
All right, I just have 3 last points. Tomorrow we got a star party. Please, if you can be here, be here. Next, the week after, we have a Christmas party. If you haven't given your email yet to George, please do. Thirdly, after the meeting party tonight at the Village Inn, we have a group of us that typically get together for Village Inn for pie and whatnot afterwards. So
Any word about the jackets?
from what I understand, they have been ordered. So Alan will be reaching out to those who ordered those. So other than that, I don't have anything. Does anybody have anything else, Fred?
Any more of these that's still out there, please hand them to me, the visitors cards. And if you haven't filled out the attendance sheet, please do.
All right. All right. Meeting adjourned.
8:30, brother. Look at that.
We got a